is maybe a special day for this foundation seminar. Not only do we have our distinguished speaker here, but we have who's a distinguished philosopher of physics, though he doesn't really call himself that anymore, maybe philosopher of religion and mathematics. Or
actually, hockey player.
But we also have two other distinguished philosophers of physics who happen to be the teachers of this guy, Bill Demopoulos and Jeff Booth are both here. And they came to give him, I think, as much trouble maybe as they did when he was the graduate student, just Professor Allen.
Are we going to treat this as like a PhD? Reaccreditation.
Well, thank you very much. I'm really happy to be here. I don't know whether this is making noise or not. I think I turned it on.
I think it is.
Okay. There we go. Okay. Yeah. What I'm going to do is I have a sort of a nightmare about this because I keep thinking that there's something that's really obvious here, and perhaps, especially to physicists, I don't know. And yet, it seems to me when I get into conversations with people about parts of this that whether it should be obvious or isn't obvious, a lot of people are inclined to fall into what I've sort of called here the EPR illusion. And what I mean by that is just that there's something about the EPR argument that is very tempting, even when we all know that it can't be right, and even when we could all trot out on the back of an envelope any number of proofs that it isn't right, and yet somehow there's something very seductive about certain parts of the reasoning. The way I got to thinking about this, actually, I should give some proper credit here. Chris and Carlton Case and Whittaker Schack wrote a paper on quantum certainty that I dare say many of you know, in which they made use of a little argument that I gave back when Moses climbed the mountain about 30 years ago, I think. And I was intrigued by the use they made of it, but wasn't quite convinced. And so I set to thinking about that, which then led to thinking about the connection between that and the EPR argument. And so in some sense, I suppose Chris is the godfather of this paper, whether he likes the result or not. And what I want to say is that once you start looking at the EPR argument in the way that I'm inclined to now, it softens you up for a way of thinking about quantum states that at least didn't come naturally to me at first. And so that's what I want to do. I want to sort of break things into two parts. I want to sort of step through, in a way, a very elementary discussion of some things about the EPR argument, trying to highlight things about it that seem to me to lead us off the rails. And then I want to say a few things at the end about what this might have to do about how you think about quantum states. And then we will see what folks have to say. Oh, sorry.
Being wrong, and so you're going to explain what you mean by that?
Well, yeah. What I mean is that EPR, at least on one way of reading it, I think on Bell's way of reading it, they're trying to convince us that the quantum system has more properties, as it were, than the quantum state would allow. And in particular, they try to convince us that, in the case of the argument as they give it, that there is an element of reality for position and an element of reality for momentum for this distant system. And my point isn't that they're right or wrong about that. Actually, I would be happy to take a view on that if pressed. But my point rather is that whether they're right or wrong about that, the way that they get to that conclusion can't work. So what I'm trying to do here is make the case that whatever you think of their conclusion for other reasons, the argument itself can't work.
Okay. Are you going to describe that, or is that a premise for your talk?
No, I'm going to try and describe it.
Okay, good.
In other words, I'm going to say that in some sense, I think Bell's diagnosis is right. that if you want to put together all of the things that seem implicit in the EPR argument, you have this sort of unsavory brew. It can't all hold up. But that there's a way of finding yourself not tempted to go that far long before you get to an argument like Bell's. And so what I want to suggest is that there's something peculiar about the reasoning, and that it starts with the criterion of reality. I want to suggest that there's a problem with the criterion of reality, the way we use it. I'm not here going to take a stand on things like, say, Lowmean mechanics. If someone likes Lowmean mechanics, that's fine with me. I'm not trying to make a substantive case for a particular interpretation, but rather to say there's a way of looking at things that I think comes fairly naturally to many people that gets EPR in trouble quite a bit before one might have thought. At least that's the way it seems to me. So, just a reminder, a little sketch of what they say. They say, when you consider this state, written in the orthogonal form, where you can decompose it in two different ways. They pick position and momentum as the quantities that they're interested in on the right, but we're not going to care about that. It isn't going to matter what they are. And so we've got these two quantities, A and P, for the first system and the second. We'll refer to them as parallel. Likewise, two quantities, B and Q. And they don't commute, but we'll refer to these quantities as parallel. And another caveat I should add here, which I'm not sure I put in one of the slides, is that if you are interested in the exegesis of the paper itself, if you're worried about what were EPR really saying, how do we best understand the actual text of the argument, that turns out to be a surprisingly tough question. I can't do any better than refer you to the stuff that Arthur Fine has written on this. I think he's made the case that there's a lot that's not obvious about just what the text is really up to in various places. But I'm going to set that aside, because my thought is that there's a kind of an argument we sort of carry around under our hats, so to speak. And it's a very EPR-like argument, whether or not it's exactly what that paper had in mind. And that's what I'm interested in, this argument that we carry around under our hats. So just to sketch roughly the way that I think they see the argument, well, OK, if Alice measures A and finds some value AK, she can predict the outcome of a P measurement for Bob. But this measurement that she makes on system 1 doesn't influence system 2. That's what EPR assume. And therefore, this p-value was discovered rather than created. And furthermore, had she measured B, she would have discovered a Q value. And therefore, not only does system 2 have a p-value, which we're going to sometimes refer to as an element of reality, as they do, but it also has a Q value. But no quantum state can account for both. No quantum state can give you simultaneous values for this P and Q. And therefore, the quantum state must be incomplete. It must not tell you everything there is to know about the system. So that's all familiar enough. Now, the thing that I'm going to focus on here is something that philosophers sort of like to talk about, and that may be a less familiar way of talking to physicists. I don't think there's anything complicated here, but I will try to be mindful of the fact that the lingo that comes naturally to me may not come quite as naturally to some other people. But the basic point is this. If you're going to talk about these elements of reality, this much I'll say is very clear from the text. Among other things, you're saying things about what would happen were P measured. If I attribute an element of reality to P over there in that second system, I am, whatever else I'm doing, saying something about what would happen if P were measured. And so, for purposes of this talk, I'm not going to distinguish among these things. There might be reasons in other contexts to do that, but having an element of reality, having a value, satisfying the obvious measurement counterfactual, I'm just going to treat those interchangeably. And I'm going to put the focus on the counterfactuals because I think that's where things go wrong. Because I think when you start thinking a little more clearly about them, then this illusion, as I refer to it, starts to dissolve. So let's just introduce some distinctions here that are simple enough, but that maybe not everyone's familiar with. three kinds of conditional statements. One philosophers often call would counterfactual. So for example, if X were measured, the result would definitely be X. But then you might consider something weaker. If X were measured, the result might be X. Okay? And then finally, there's this very weak thing. If X was measured, the result was X. And the tense isn't what's important here. Okay? It might be is measured, will be measured. But as a particular kind of statement, this and this are different. You might not think at first that they're that different, but as we'll see, they are, and I think that the examples will make the point. But we'll say a little bit more. Okay, so just some notation. This is fairly standard notation for people who talk about this stuff. So this thing here, this little box with the arrow, this says if F were true, then G would be true. But when you've got the little diamond, by the way, for those who know, in talking about possibility and necessity, logicians often use the box to mean some kind of necessity. The little diamond means some kind of possibility. And so this says, if F were true, G might be true. So, and I made a typo there, for which I apologize. This should say might. Okay, if F were true, G might be true. And as it turns out, we won't dwell on this, but I'll just mention it. Think about this. Suppose someone says, well, okay, if I were to measure A, the result would be AK. And someone says, no, I disagree with you. I think you're wrong. What are they saying when they disagree? Well, the usual way for people to do the logical stuff to think about this, what they're saying is, no, if you were to measure A, you might not get AK. So these two things are interchangeable. We won't need to deal with that, but that's just how it works out. And then finally, there's this weak thing. If F is true, G is true. Or if F was true, G was true. And this is simply the so-called truth functional if-then. What it really amounts to is this. If I say if X, then Y in this sense, all I'm saying is this. Either X is false or Y is true. Put another way, it is false that X is true, but Y is not true. So this is very weak. One way to think about it roughly, what I mean is that, well, another way to put it is this. Suppose, as we will throughout here, that the F here is possible. If you consider the case where F is impossible, then it turns out that this is degenerately true. It's a degenerate case. So stay out of the degenerate case. Then what you have is this. This implies this, and this implies this, but not vice versa. Yes?
Suppose you could measure F, but you just don't, as it turns out. Then is 3 true? And
that's actually exactly right. It turns out that 3 is so weak that if I say, okay, consider this statement. If A is measured, then the result is AK. If A is not measured, that actually turns out to be true. That's how the truth functional conditional works. Now, parenthetically, and this is not something we need to bother with, I'd actually be willing to make an argument that, believe it or not, ordinary English, if then, in many cases, works that way. But we don't need to worry about that. That's another story. So a rough way to think about it is this. When you have something like this, if X were true, then Y would be true. This suggests something like a deterministic or law-like connection. Okay? Whereas when you have something like this, if X were true, Y might be true, but also if X were true, Y might not be true. When both of those hold, you've got something more like a non-law-like or indeterministic connection. So that's the background. Okay. Now, a couple of principles here that might seem on the face of it to be the same thing, but they're not. So here's something that's trivially true. If F were true, then either G would be true or it wouldn't. Okay. If I were to make the A measurement, I'd either get the result AK or I wouldn't. Okay. I'd argue that. And that's just a way of saying that the law of excluded middle would still hold even if F were true, and we'll call this counterfactual excluded middle. For example, if X were measured, as I said, I would get the result X and wouldn't. On the other hand, This isn't trivial at all. Let's go back. Okay, there's that. And then there's that. And they might kind of sound like they say the same thing, but they really don't. So consider this. Is it really true that either if x were measured, the result would definitely be x, or if x were measured, the result would definitely not be x? I mean, one way to think about it is this. One way to convince yourself that that's not so trivial is that, well, for the or statement to be true, one of these things would have to be true. And at least intuitively, that means that there'd either be a law-like connection between making the measurement and getting one result, or a law-like connection between making the measurement and getting the other result. And when you think about it, that's not really very plausible. So this principle here, called counterfactual definiteness, is not trivial, but we have a tendency just to kind of elide between the two. And it's not hard, we can talk about this later if need be, to go back in the literature and find cases where people did exactly that, where they elided between these two principles and where it got them into trouble. Okay, and by the literature here, I don't mean the philosophy literature, I mean the foundations of physics literature. Yes? The previous one was called counterfactual excluded middle, because excluded middle is just, one would hope, a triviality. And this is counterfactual definiteness.
It should say F and not X in the previous.
Oh,
The law of excluded middle would hold if X were true, it says.
If F were
If F were true, absolutely, yeah. My apologies, I didn't enter these slides as well as I should have.
And can you emphasize something you did
Sure,
in
yeah.
my office? That
Yeah.
if this were the usual truth value connected, then these two statements.
Good, yes. If instead of this, if F were true, then such and such would be true, we just put if F is true, then Y is true, then counterfactual excluded middle and counterfactual definiteness would turn out to be the same thing. But I want to emphasize that it's really not important for purposes of what's going to follow here to worry much about the sort of inner workings of the logic, because I think that what you'll see is that as you go along, the sort of examples are kind of intuitively compelling on their own. You don't need to sort of think about this from a logician's point of view or something like that to get the point. So we've got counterfactual excluded middle, trivial, counterfactual definiteness, not trivial, and the difference between them is going to matter here. Now, just something about EPR and counterfactual definiteness. Counterfactual definiteness being among these things. There's a definite fact about how the measurement would turn out, so to speak. The way that I think about it, the person that EPR is arguing with is someone who, at least in a weak sense, thinks about quantum mechanics indeterministically. That is to say, at least they think this much. Typically, when you make a measurement, there's nothing that fixes the result in advance. And so, in a sense, part of EPR's job here, in the case that they're dealing with, is to convince them that, well, at least for these examples, you've got to say something stronger than that. And so one way to look at the project is, does the EPR argument, if you look at it carefully, really provide sufficient intuitive motivation to make that move? Okay, and the suggestion is going to be that it doesn't. So that's our question. Does EPR give what I'm calling the orthodox indeterminate, someone who thinks of quantum mechanical measurement typically indeterministically, but has a pretty orthodox view of the theory, at least orthodoxy circa the time that this paper was written. Does the EPR argument really give that person much of a reason to change her view? So what I'm going to do here is I'm going to work through a sequence of 4 very simple cases, and I'm just going to say some things about them that I hope will be, in most cases, intuitively pretty plausible, but suggest that if what I say about them is intuitively plausible, then the end result is that, as I said, the EPR argument no longer seems compelling long before you get to 1964, long before you get to Bell-type results. So here's a warm-up case. A single particle. And suppose that you take the point of view that the orthodox indeterminist does, that the outcome of some measurement, this A measurement, is not determined by anything in the past. So Alice measures A and she gets results. She gets OK. And just because sometimes it'll make the notation a little more compact, I'm going to use this fancy X for this thing. A was measured at Xi, and the result was AK. Okay. Xi is a point on the space-time diagram, as it were. Yeah, right. Yeah, it's a space-time point. Now, the orthodox indeterminist is going to assume that, unless there's something going on in between, if you repeat a projective measurement, you get the same answer. We'll just sort of take that as given. And so now consider this. The measurement was actually made at Xi, but we can sort of ask ourselves this. Well, suppose that at a point, suppose we think about a point omega that's a little bit earlier, okay, in the causal path, just a little bit earlier. Here's what the determinist will say. Two things. Okay, the indeterminist made her measurement at Xi. She got the result AK. And she will say this. Well, if A was actually measured a little bit before, if there was an additional measurement a little bit earlier than the one I made, then the result of that measurement was AK. Just because you repeat a projective measurement, you get the same result. Okay, so that seems harmless, innocuous. But she won't say this. Suppose that, in fact, there was no measurement. She won't say if A had been measured at omega, the result would have been AK, because after all, she doesn't think that anything fixes the result of these measurements in advance. So had the measurement been made a little bit before, it might very well not have turned out AK. And in fact, this will come up a little bit later, had the measurement been made a little bit before, it might have turned out AJ, and then her measurement would have turned out AJ. Okay. That seems, I think, pretty commonsensical from a certain point of view. It's what I might call sort of quantum common sense. All right. So, just to emphasize, she'll accept this innocuous, straightforward, indicative if-then. She will not accept the counterfactual. Yes?
But of course, this argument depends on the state. If the state is an eigenstate associated with eigenvalue A.
Right, and I'm assuming it isn't. Right, yeah. I didn't bring the eigenstate word in here just because I wanted to say as little as I can about states until later. Yes, absolutely right. I'm assuming it's not.
That would be a crucial point in the EPR argument because you have an eigenstate essentially.
You have an eigenstate. Well, the initial state isn't an eigenstate of anything you measure.
After the first measurement.
And well, we'll get to that. That's why I didn't want to talk that way. Yes, right. Yes.
So I assume she won't also say if A was, she wouldn't say that if A had been measured at C, then the result would have been A. In other words, the place that it really was measured, she still wouldn't give this box arrow.
Well, since it actually was measured at C, it turns out that trivially, had it been, we would have gotten the same result.
So the way you define it, you do have this box.
But that's only because you're talking about an actual case. In other words, in the case where the A part really is true, the counterfactual and the ordinary if-then collapse into one another. It's only in the case where it's genuinely counterfactual, where A wasn't measured at omega or psi or whatever, the difference comes out. Yeah. Okay. But notice this. I mean, I think this is right. The indeterminists will accept a conditional probability statement like this. The probability, given that A was measured at, sorry, here's where I tricked myself up. Forget the notation. Let me write on the board, if I may, what I meant, because the psi has an index number. It isn't supposed to be this. Here's what she'll accept. The probability that a measurement well, it isn't actually going to matter. We're fine. We don't need to worry about the index. She's going to accept this. Let me write out one version right here. Yeah, I'm not quite sure what I was thinking when I wrote
And did you just
that.
want to say that if you measure the same thing twice, do you?
Yeah, yeah, I just thought I might write it
Well,
out.
then it's right. What you have in your slide is right.
What I wanted to get at is this, is that, yes, you're absolutely
Because
right,
X
but
is
we need
ACN.
the index here.
Yeah, you need an index
Yeah,
there.
so what I need here is just to change that. The point is just, it's exactly what Jeff said. The probability, the conditional probability, she got the result AK when she made the A measurement XI. She can ask a conditional probability question about an A measurement a little bit earlier. What's the conditional probability for getting the same result? It's 1.
For another
Okay, so
one.
just add an index omega to that.
But, I don't know.
That's not,
Can you say in words what?
yeah. I asked, okay, Alice has made her measurement at Xi. She's got the result AK. And now she's going to check to see what Bob is up to earlier. Okay. And she might find that Bob made a measurement earlier. And she's going to make a bet on the outcome of that measurement, or conditional on what she done and Bob actually making the A measurement earlier. So just in other words, add an omega there. And then she's going to say, well, the probability that that outcome is AK conditional on this is just 1. It's just a point that when you repeat the projective measurement, you get the same result. Yes?
So should the little AKs have omega or C subscripts on? Or
They should actually have another index, which I suppressed because it was getting ugly to write, but you're right.
Sure.
It
So
really should be.
in this case, that would have.
So that would have an
index of omega.
uppercase, the other index would be omega. Right, exactly. You have an omega here for the earlier measurement of omega and an omega here for the result. Yes, exactly right. That's exactly right. Yep. So,
Anyways, it seems to me that that's not a valid argument in the classical picture, because I can imagine if I just have some vector on a sphere that's rotating in some random way, and I measure it at some time t, and I get some outcome, and maybe the physics of that device is such that successive measurements give the same outcome. That doesn't mean had I measured it momentarily earlier, I would have had
you
that
used
same
a
outcome.
counterfactual, and I didn't. Notice, that's important. It actually turns out to be the number method.
Oh,
This isn't a counterfactual, this is just a conditional probability.
I was just saying that you did perform
Yeah.
the earlier measurement.
I'm saying if I condition on these assumptions,
I see.
on Alice, I've made my measurement at Xi and I've gotten AK, and then I condition on the further assumption that Bob made a measurement earlier of the same observable, then I'll give you, I'll bet the house that
All right.
the result is this.
All right. I thought the earlier measurement
That's
was a
correct.
counterfactual.
Yeah, but I'm not using a counterfactual, and that's deliberate. Because I'm saying that, at least initially, probabilities like this are all that quantum mechanics gives you. And so what we have here is a conditional probability of 1. The measurement we're reasoning from, Alice's measurement at Xi, does not influence the measurement we're reasoning to, Bob's possible measurement a little bit earlier than omega. But we are not entitled to infer an element of reality at that earlier time. We are not entitled to infer. Remember the situation. The situation is Alice has made her measurement. She doesn't know what Bob's been up to. Maybe she's going to collect Bob's notes a little bit later and look them over. And so, if it turns out that Bob made that measurement, she's going to bet in advance what the result was. But that's not the same as saying that if it turns out that Bob didn't make that measurement, she knows what would have happened if he did, if he had. She won't say that. She won't say that at all. So she will not attribute an element of reality to the particle at that earlier time for A. She won't say that there's an A element of reality at omega. Not unless it turns out that Bob actually did make the measurement. And then the element of reality amounts to nothing more than the measurement result. She will not. Look, there's a slogan that you've all heard that's not quite what I have in mind, but it might be helpful to keep it in mind that unperformed measurements don't have results. I wouldn't quite want to put it that way.
And this is the little bit of overlap between
Yeah.
between your way of thinking and the cave's in shock and Cook's
Mhm.
way of thinking.
Yeah, right,
We would both agree on this statement.
yeah, yeah,
We four would agree on
Yeah.
this statement.
yeah.
Can I just to make sure to really understand that,
Yep.
to sort of put it in words? I mean, suppose the X measurement occurs at sort of 12 noon, that's Alice's measurement.
Yep.
And Bob's measurement at like 10 to 12 or something.
Assuming it occurred well, yeah, right. Whereas it's
Yeah, yeah,
10
so-
minutes before
so,
12.
yeah, we were saying 10 minutes for 12.
Yeah,
So this
right.
statement says the probability that Bob's outcome at 10 to 12 is AK, conditional on the following things.
Yes.
Alice made a measurement at noon and got the outcome AK, and Bob made a measurement at 10 to 12.
Exactly right.
Okay.
Exactly right. That's exactly what it is.
Okay.
That's
And that,
exactly what it is.
yeah.
Yes.
I mean, are we dealing with an indeterminist here who would insist that the moon isn't there when you don't look and things like that?
No, not at all. No. The indeterminist is perfectly happy with there being all kinds of things in it.
But
The indeterminist is told.
couldn't the indeterminist insist and that we couldn't refute that the moon is not there when no one's looking? Isn't that
That's,
possible?
look, that's an interesting, I take the point you're raising. It's a puzzle, but it's a puzzle, I think, one way or another, you're going to be stuck with. So one way that you might put it, there might be two ways of reading what I'm going to say here. One way to read it would be to say, well, if you're an indeterminist, here's how you respond to the EPR argument, and this just means that there are certain things that we might otherwise be inclined to say that we're not going to be inclined to say, or you might react in horror and say, well, I guess we better not be indeterminists. I mean, you can look at it in that way. But in any case, what I want to do initially is I want to say, look, what would an indeterminist be inclined to say here? Yes?
Okay, so this probability follows from your implication that you know that Bob did, on your previous slide, you had the implication without the little square, and you said that the indeterminists would accept this. So this probability assignment follows directly from that.
Well, you might say it follows from that, and you might say that it just follows from the principle that if you repeat a projected measurement, you get the same result. That's really all it's being said. It's as I said.
So what were you saying that she wouldn't accept that if she
won't.
knew that he
Yeah.
didn't perform a measurement, then
She will say this. Suppose, let's put it in two ways. What will she commit herself to? And then we might ask what's actually true, whether she's in a position to know or not. But let's start with what she'll commit herself to. She's made a measurement at Xi, she's gotten AK. She will say this. If Bob really did make the same measurement a little earlier, he got AK. That's a so-called indicative. She'll say that. But she won't commit herself to this. She doesn't know whether Bob actually made a measurement. Maybe he didn't.
Oh, I see. So,
Right.
so you're saying she won't assign the probability if that A isn't appearing in the conditional.
No, what I'm saying is that I think there's a tendency to think of these probabilities in quantum mechanics as being about counterfactuals. And I think they're weaker than that. I don't think they are. I mean, parsing how best to translate, there's this, you write a conditional probability, and maybe what you want to say is you want to turn it into a conditional statement. And there's no simple way to do that. I mean, it just doesn't work nicely. But maybe when we get to some of the other examples, we'll have another reaction. But yeah, okay.
Maybe you're coming to this, but will she say, if Bob makes his measurement counterfactually, if Bob were to make a measurement at 10 past 12, then you will get it.
Yes, then it will. Yeah, that's right.
You will say that.
Yeah, I would say that because
Say that. So
well,
there's
one way to think of it crudely, we can say more about this later, but she's made her measurement. You might think of that in the sense as acting as a state preparation.
Right. But now there's going to be some apparent conflict with Lorentz invariant. I mean, if Bob
Well,
has space like,
we'll
coming to that.
get to that. Although I don't want to actually talk about it quite in those terms, but yes. So,
I guess this is clear, but I mean, some people are puzzled. Perhaps the whole thing could be put just very simply this way. I mean, you've got Alice and Bob in an EPR situation. Alice makes a measurement and gets a result. Bob says, hey, I made that very same measurement 5 minutes ago. She says, oh, well, then I can predict
Then I know what you're
probably
saying.
one what your outcome.
Right, exactly
But
right.
if he says, well, I actually didn't make a measurement
Right.
at all, then, and she says, well, I can tell you what you would have got if you had. I mean, that's not correct.
Right, that's exactly right.
Because
That's
his
exactly
situation
right.
is got the fingertips,
Yeah,
and that's
that's
the
it.
point.
That's exactly right. Bob says, gee, you know, I made an A measurement a moment ago. Then she will bet the farm on what the outcome was. He says, oh, this is the first time this particle was measured. I didn't make a measurement. She will not say what would have happened had he made a measurement. But there's still a simple conditional probability. I think conditional probabilities are weaker. We might be inclined to think of it as being. That conditional probability is still okay. But let's continue to an example that kind of closer to the heart of the matter, perhaps. So here's a little diagram. So Alice is over here in system 1, Bob's over here in system 2. I've labeled these points pi for past, u for now, and phi for future, okay, along the path of Bob's particle. And so here's what we have. We have them in this correlated state that we showed at this entangled state. And one is first measured here, not measured before, and the result is as before, A is measured, the result AK. Particle 2, if it's measured at all, is measured at most once. That's just to sort of make sure we don't have jump going on in between that messes things up. Okay, now, keep the diagram there. Now, remember, the holding constant for this example, A was measured at this point, and the result was AK. Just keep that in mind. So we can say this, the indeterminist will say this. If P was actually measured back here in the causal past at point pi, you know, as Jeff said, we imagine later on Bob comes up and says, gee, I made a measurement there. Alice will bet the farm on what the result was. She will say, in any case, if P was measured at pi, the result was pk. She'll be quite happy to make that weak conditional claim. But let's just imagine, as it turns out, again, figuring the way Jeff did, Bob comes along and says, I didn't make a measurement. She will not say this. She won't say, well, Bob, if you had made a measurement at pi, the result would have been pi k. You wouldn't expect an indeterminist to say that, because the indeterminist is going to say, nothing fixes the result of the measurement, typically, before it happens. Yes?
Shouldn't you say, if one would have made a measurement then, and I would have found result AK later, then this measurement necessarily would have happened?
No, not even that. Not even that. I'll say more about that later, but no, not even that. Well, no, hold on, sorry. I may not have parsed correctly what you said. Yes, if you put all that stuff together. Yes. Okay, I was, yes. No, absolutely right, yes, absolutely right. I was mixing your point up with a slightly different one I want to make later. Yes, that's right. So if I ask this kind of actual question, suppose Bob had made a measurement at pi, and I still had made a measurement at psi, and still had gotten the result AK, would Bob's measurement then? Yes, in that case it would be okay. Yes, right, thanks. Yeah.
Well, I'm sorry, I missed what you said, and I don't think you finished it. What?
Sorry. The question was to consider this counterfactual. If, Alice says, if I had made a measurement just as I did at psi and got AK, and Bob had actually made a measurement at pi,
Yeah.
then the result Bob would have gotten would have been pk. That one's okay. That just kind of is the extended version for the entangled systems of the repeat the measurement kind of thing. I'm not sure I quite want to put that. That would be okay. Yeah, she would say that. Another way to put it is this: is that she's thoroughly confident But in any case that you look at, you're going to observe the correlations. If both measurements are made, you're going to observe the correlations. So take a counterfactual, we're taxing to the counterfactual that both measurements were made, and that we have the result of one of the measurements. Well, then she looks at the counterfactual and says, you get the result that you expect. Yes, she will say that. But she won't say this. She won't say that if Bob didn't do anything back there at all, sorry about that, that she knows she can accept this. She won't go for the counterfactual. She won't say, in case that Bob didn't make an earlier measurement, what would have happened if he had.
You're up on a new case.
Or did I?
You're not back behind.
There we go. All right. Sorry.
Right there.
There
There we are. Good. Okay, so we were here, now we're here, and she'll say this. This is what she'll say. I wish I could make that go away easy with my trackpad turned off. So she'll say this. No, she'll say, look, if Bob had made his P measurement at pi, he might have gotten PK, but if he made the measurement at pi, he might not have gotten PK. She'll say both those things. Because she's an indeterminist after all.
Can you make it full screen again?
Yes.
For those of us with old eyes.
Yeah, in fact, actually, you know what I'm going to do? The moral of the story here is avoid using Windows wherever possible. I'm sure you all do that anyway. So we'll see if we get back.
Right.
All right. So now we're going to go to a different case. But let's just say a few things about this one in summary. So here's what the indeterminists will say, that if EPR are correct, their argument should work in the backward-looking case, just as well as it should work in the space-like separated case. The logic of the argument doesn't change. You've got the same conditional probabilities. You've got the same conditional probabilities. You've got the same quantities. You've got the same story. The only difference is that in one case, you're running the story about the past, and in the other case, you're running the story about something that's space-like separated from you. But the premises that EPR give you have the same form, have the same structure. So if the argument is going to work at all, it should work in the backward-looking case. In the backward-looking case, Alice should be able to infer an element of reality in her causal past from the measurement result that she gets at Xi. And the suggestion here is no indeterminist in their right mind is going to say that. No indeterminist in their right mind is going to feel compelled to say that. So what we see here, and one quote in one sense, just to stop here and say we've already refuted the argument, but I don't think that would be the thing to do. But let's continue. So she's going to say, if EPR were right, their argument should work in this case. You have the relevant probabilities, you have no disturbance, but it doesn't work. So just as an actual result, Xi doesn't fix a merely possible result on the same particle a little earlier, so an actual result of Xi in general doesn't fix a merely possible result in the causal past. Okay? Now, let's go in the other direction. Let's go forward-looking. Okay? And here, you might say something different, but we'll see that it may not matter for other reasons. So again, we're going to suppose, as we have been doing consistently, Alice measures A at Xi, she gets result K. And let's suppose that system 2 is not measured at any time before 5. Maybe it's measured there, maybe it's not, but it's certainly not measured before. So here, once again, we can say this. Alice will say if P was measured at 5, or will be measured at 5 as a number, then the result will be PK. She will commit herself once again to this very weak so-called indicative condition. But now the question, and we also have, of course, this conditional probability. Conditional on her actually having made the measurement she made and getting what she got, AK, and the further assumption that Bob measures P at 5, she'll bet the bottom that his result is PK. We got that. Once again, we have the EPR kind of premises for the criteria of reality. Question is, should we accept this or not? That's what you need if you're going to have the element, okay? Idle curiosity. I've never asked this question before. Should we? Who says yes? Who says no? Who says maybe? All right. I feel like I'm in my logic class where I was talking this fourth possibility. I never quite figured out. Well, actually, what I'm going to say, the indeterminists might be quite willing to say that. I'm not going to insist on that. If someone talks me out of it, I'll be happy. But I'm going to say, I don't mind, and I don't think it creates any trouble, but it doesn't help EPR. Okay, so let's talk about this. So one reason I think that you might be willing to go along with this is that, after all, we're talking about something in the causal future, so we're not going to get Magpie paradoxes and things like that. We don't need to worry about those kinds of problems. And you can also imagine this. You can imagine her getting on the phone and calling Bob up and saying, Bob, if you need a particle that we measured for P will give the result PK, I have got a particle for you. And Bob would be inclined to think, okay. And he'd be inclined to think that even if he doesn't bother to make a measurement, he knows what would have happened if he did. So I don't have any problem with accepting the counterfactual data. The question is, does this get EPR what they want? And I would suggest the answer is still no, for a rather different reason, but nonetheless, you still won't get the EPR working. So, first let's start with the question of simultaneous values, because EPR are trying to convince us that there are simultaneous values to P and Q. We conceded that Alice might be prepared to infer a P value. What about the Q value? Well, here's the problem. Suppose Alice had measured B instead of A. That's what we're going to have to think about if we want to reason about the Q value. Well, we don't have this. So let's start with what we do have. We have this. If Alice had measured B instead of A, xi, then the result either would have been B1 or probably B2 or whatever, how many values there are. That's okay, that's fine. But that's just counterfactual excluded middle. That's trivial. But we don't get from counterfactual excluded middle to this. We don't get, well, either if Alice had measured B at psi, she definitely would have gotten B1, or she definitely would have gotten B2, or however many other orders we need here. We don't get that. Okay, in order to make the inference to there being some definite element of reality for Q over here, you have to have the truth of one of these bits here, and the indeterminist is going to stand before it. I think quite reasonably saying, no, I don't. There's no fact about what would happen had I measured B instead of A. And so there's no basis for making the inference to Q over here. It's not just that there's no basis, I've got no reason to agree that there's any such fact at all. Okay, so the first thing is that even if we allow the inference from the A result here to an element of reality for P in the future here, this does not get part of what EPR needs. It doesn't get simultaneous P and Q. Okay. Second thing, this is a little perhaps further out there, but it seems to be worth considering. What about no disturbance? It's part of the condition that you need to get this argument going. You say if, without in any way disturbing a particle, you can infer an element of reality, then blah, 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 blah. By the way, just parenthetically, this actually comes closer to what Einstein himself had in mind. Einstein was not worried about pairs of simultaneous values. I think one of the interesting things to say about this. He thought the problems came up in the case of just thinking about one measurement of one quantity. Well, suppose then that the indeterminist says, okay, yeah, I'll buy it. My AK result here lets me infer this counterfactual of the future. Now, consider this. Suppose Alice says this. I made my measurement at psi, but suppose I'd made the measurement a little earlier at omega. Okay? Same measurement, but I just made it a little earlier. Well, in that case, I might have gotten AJ rather than AK. And if I had made the measurement a little earlier and gotten AJ instead of AK,
I would infer not this counterfactual, but this one, a different element of reality. In other words, insofar as Alice is prepared even to concede that she can infer the P element of reality here, it's going to turn out to be oddly sort of bound up with when she decides to make her measurements of the speed. Had she made her measurement a little earlier, it might have turned out that there was a different element of reality associated with that future point. Now, is this a case of causal connection? I don't know. In the paper that this is based on, I sort of throw out the word causiness, or Stephen Colbert's truthiness. Okay, because I'm not quite sure the right way to think about it. It's kind of cause-like, but it leaves you uncomfortable with simply declaring flatly and unequivocally that the no disturbance condition, no influence condition is satisfied here. You should be nervous about just going along with that.
Well, I think that shows you why Alice wouldn't accept
It might be.
the counterfactual at the time.
Yeah,
as those quantum basics wouldn't accept it either.
Poor guys, yeah. I think that's one way you could go here, and I don't mind, as as you and I are discussing, I don't have any strong view about this, but I would just add this. I think that many ways of looking at causation, there's much less to causation that meets the eye anyway. And so it might not be as disturbing as you think if you think about causation in some way. But I don't really have anything any access to growing here. Okay, so you don't like this conclusion? Well, you can avoid this conclusion, as Chris just pointed out, by refusing to make the first inference from the A, K here to the counterfactual there. But if you do that, then the EPR argument doesn't get off the ground, because you can't infer the element of reality in the future case. So you shouldn't know it. So, summing up what we said so far, you got to infer simultaneously. To infer simultaneous values in the forward-looking case, you need to accept counterfactual definiteness in a case where the indeterminates are going to say, no, I'll go with counterfactual through the middle, but that's not strong enough. You need counterfactual definiteness. I'm an indeterminist. I don't believe in any such thing. If you accept the inference from Alice's A measurement result xi to this future counterfactual, then you should get nervous about the no disturbance or no influence issue. I say it comes into doubt. I don't want to come down hard, but it's a worry. And if you reject the inference at all, then the argument doesn't get started. So, what we say by way of sort of an interlude here is the indeterminist has good reason to reject the EPR argument in the backward-looking case and in the forward-looking case. It would be very weird somehow if the argument worked out in the space-like separated case. It would be somehow intuitively puzzling if the argument was bad in both of these cases. It would be good in that case. Suppose, to move to this case, that Alice, once again, assumes she measures A here with result AK. Particle isn't rated over here before mu. Once again, we have this familiar indicative conditional. We have the familiar conditional probability that the EPR argument is based on. Should we accept this? Now we're in the spatial separated case. Well, we said in the past case you shouldn't. In the future case, maybe you should, but you're not going to get EPR's full conclusion if you do. What about here? Should you accept it? Well, my inclination is to say no. But it will turn out that whether you think the answer is no or yes, it still doesn't help EPR. We could come at it this way. Suppose this is before. Is this counterfactual about the elsewhere more like the one about the future, or is it more like the one about the past? I don't know that there's a basis for having strong intuitions here. My intuition, such as I have one, is more like the past. Because there's a couple of ways this is more like the past. If you're worried about making inferences to the past here because you're worried about getting in trouble with relativity in some way or another, then you're going to have that same worry here. The kind of thing that made it plausible to consider the counterfactual here was stuff like the possibility of telephone bomb. Can't do that here. So it seems to be more like past case, don't accept the counterfactual. But suppose that you like the counterfactual. Well, then what I'm going to say is simply this. The kinds of arguments that I ran for the forward-looking case just get repeated here. Even if you somehow think that the result allows you to infer the P element of reality, you're stuck with the fact that Alice didn't measure P, and she's going to say, look, there's no fact. And so there's no basis for inferring that there's likewise a Q element of reality. Furthermore, if you found anything compelling at all about the worries about influence, they're going to come up here again. The argument that we ran before about the forward-looking case where Alice says, well, gee, I made my measurement here, but suppose I made it a little earlier. Then I might have got a different result, and if I had, I would have inferred a different element of reality. Should make you nervous once again. Okay? So you've got the same strange dependency. And so, depending on how much time we should take, Chris, this may actually kind of be a place to start. But let me just sum up what we've got so far, and then maybe other things will come up in the discussion. But I will let you explain. The rest of it, I can probably go over a few slides very quickly just to throw out the thoughts, but please feel free to stop me when that seems appropriate.
Well, why don't we just do this? If anyone needs to leave, walk out when you need to leave. And otherwise, I'd say go at least 15 more minutes.
Okay.
If you have to.
Okay, yeah. Okay, so what we said is from the point of view of this orthodox indeterminist, the argument fails, and fails long before we get to null-type results. Fails in the sense not of having a proof that the conclusion can't be had, but fails in the sense of starting with some premises that I think a lot of people on reflection will find plausible, perhaps even orthodox sounding. The inferences no longer command your assent. So if I'm right, then there was a sort of an illusion here which has been sort of perhaps dispelled. So accepting something like this x and these conditional probabilities equal 1, which is the fact doesn't give you an element of reality system 2. Now, what I wanted to do in the rest of it here, and we'll just try to say a few things about this quickly, is suggest a few things about states and what thinking of things in this way might.
Did you need a probability equals 1?
I did. Oh, yeah, right, yeah. Pardon me, terrible proofreading, yeah. Yes, this should, of course, be equal to 1.
Perfect.
Well, one of the things that let's just skip over this. This just says that the indeterminists can think about correlations as kind of just, they're just kind of given. It's just a kind of fact about the world that you get these correlations without there being underlying elements of reality that they speak on. It's a bit like Merlin's business about correlations without correlata. I'm not entirely happy with that way of putting it, but it's a somewhat similar point. But thinking about the state, after thinking about this, I came to say things like this to myself. I don't want to say that quantum systems always have quantum states, because I'm going to end up thinking of the quantum state in that realistic sort of way. May not be that appealing. Anyway, and I don't think that when you ascribe a quantum state to a system, that means that you're ascribing an element of reality. And so let me just say something about that. Start with the old-fashioned idea of the eigenvalue eigenstate link. Okay, you all know the story. If you accept it, we start to say that the quantity x has this value little x exactly when this relationship holds, exactly when psi is an eigenstate x with the eigenvalue little x. The indeterminist, as I'm imagining her, will reject this. And here's what she'll say. She'll say that it can make good sense to assign a state without claiming that x has a value. And the reason, just in case we kind of run out of time, is because once you start looking at things like this, basically the story is going to be this. Alice makes a measurement here. She knows that Bob's been making some measurements over here. And she knows that later on she's going to get all these results together. She's going to be sort of looking at the statistical patterns. It's a perfectly good bookkeeping device for her to use, for her to ascribe the state pk to Bob's particle as a means of calculating the probabilities of the statistics that she's going to see. That use of the state is perfectly good. But in doing that, she doesn't make any commitment at all to there being some element of reality that goes with that. She gets everything that she needs by doing things in either the following way. She can simply say, I've got a joint probability here, given by psi, and I'm going to just compute the marginals, or I'm going to ascribe the reduced state to Bond's particle and do the computation that way. Either way is perfectly fine. Make it wrong. I don't think quantum mechanics cares. We don't need to take ascribing the state to be, in this kind of case, anything more than bookkeeping. But I do want to say this, and this is, I think, where Chris and I could differ. There are some cases, however, where you get pardoning out of that state. And it's this. I'm assuming that sometimes we can do stuff in the lab that has this effect. Sometimes you can live in the lab and you can manipulate the system so that you know some counterfactuals about it. As an idealization, I can go into the lab and I can manipulate a system so that I know that if this system were measured or spin in the x direction, the result would be +1. Okay. I didn't use the word state there, but I made it measure the counterfactual. No.
I don't know if this is what you mean. I mean, the classic case is if you want a system that's certainly in the ground state, you just like.
Well, that would be a good case too. All I need, the point I want to make is just that there are many such cases.
You wait and you don't measure.
Yeah. Well, but more generally, I want to get to the idea of what usually called state preparation. When I'm suggesting that the indeterminants might think of state preparation is that you're making some counterfactuals. You're doing something to the system that gives you some information about what would happen were you to perform some later measurements on it. And what I'm saying then is simply this. I'm saying that in those cases, then the only rational thing to do, so to speak, is to assign to the system the obvious item state. Otherwise, you're going to find yourself, you're going to find a conflict between the counterfactuals you're willing to accept and the probabilities that you want to assign. I could go on through some slides here and talk about the relationship between this and what's what's called the principle, but I think that would be a mistake. I probably started doing too much. So why don't I sort of take this as a place to pause and really open up the discussion? And Raphael, you're gonna.
Well, I mean, you can. This could be part of the discussion, but
Why don't we all clap first?
Well, I was confused by even the meaning of assigning a state in the relativistic context. It seems to depend, among other things, whether you're thinking in a Heisenberg picture or a Schrodinger picture.
Yeah, and I'm assuming
if you're thinking which one?
I'm assuming for present purposes a Schrodinger picture.
Okay, so but then the state has to be associated with a hypersurface.
Mm-hmm.
So if
Right.
Alice said, or whoever it was, Bob said,
Yep.
I assign a state, it's not yet meaningful, even mathematically, because you haven't specified in which hypersurface you're assigning that state.
Yeah.
That depends whether it goes to the future of Bob or to the past of Bob. Or...
Yeah, and actually, one of the things that is sort of on my agenda here, as it were, is to try to get more precise about that. But suffice it to say that a couple things here. I mean, I think for certain purposes, just kind of think of this situation. Alice and Bob are performing a bunch of measurements on a bunch of systems that have all been identically prepared, as we would say, in this state of science, in time state. And Alice is making measurements in her lab. Bob is making measurements on partial particles over in his lab. And then later on, she's going to collect all this stuff and sort of analyze the data. And I'm saying that for very many purposes, she can say, okay, the fifth run, I measured A and I got AK. for purposes of computing statistics for those cases, maybe it's the 5th, and the 19th, and 27th, those cases, I can just assign the state pk to Bob's particle, do my calculations that way, and in a sense it doesn't even matter what hyperplane they're associated with. The state, in this sense, it's a bookkeeping device. It's not, so to speak, something real. Now, there is a way of thinking about states as hyperplane dependent. Gordon Fleming has written on this, Wayne Beerbold has written on this, I dare say there are lots of other people. And I think that if you want to do that, what I say here would be reasonably congenial. But in any case, it's a backing away from the idea that when I attribute a state to this thing, what I'm doing is, as it were, attributing a property to it. Assignments of states aren't, so to speak, descriptions of particle.
And maybe I wanted to ask this later, but since you just said that, I mean, aren't you sort of going along with EPR, the conclusion of EPR, that there's quantum mechanics is terribly incomplete because it's not allowing you to assign properties
Well,
to almost anything. So
if that's what you take their conclusion to be, then perhaps I'm happy enough with it. But I don't think you could get into it quite the way that they did. In other words, what they were saying is that if you take these simple entangled cases as quantum mechanics presents them to you, and you think that quantum mechanics is okay as far as it goes, whether it's complete or not, if you at least think it's okay as far as it goes, then you're going to end up saying that particle has a p-value and a q-value at the same time. And that's, according to EPR, why you know that quantum mechanics is incomplete. I'm perfectly prepared to say that, look, we can distinguish between what I would call the quantum state, which is, roughly speaking, this sort of bookkeeping device, the sort of more epistemic kind of probability. And we can distinguish that from what we might call the ontological state, the Bohr-Einstein sort of phrase, the being in itself, the particle, whatever it's like in itself. I don't know what it's like in itself, and quantum mechanics may not tell me very much about that. And in that sense, if that's right, quantum mechanics is indeed incomplete. But the route to that conclusion is a quite different argument from the EPR one. And in particular, I think that the thing that makes us want to go along with EPR, even when we don't know, is by certain kinds of slips in the way we reason about what would happen in certain circumstances. We think that we're trying to say what would happen in certain circumstances, but we're not.
I'm not sure, but I mean, you were led by an analysis of that somehow to this conclusion that the state has no, whatever you call it, ontic significance. So
I don't think
so
that
there's some. I mean, anyway,
sure.
Maybe that you said they could have made it an even simpler argument without even doing what they did, but just paying attention to counterfactual reasoning or something. But somehow you were led by thinking about that experiment.
Well,
almost the same conclusion.
Well, I don't know if it's the same conclusion or not, because you see, notice what EPR is saying. EPR is saying that if you like quantum mechanics so far as it goes, then you're going to have to buy this argument, and you're going to have to say there is definitely something more to that particle than the quantum state tells me. And I can tell you something about what that something more is. I can tell you that there's a p-value and a q-value. Nothing like that is being said here. Nothing like that. Yes, sir.
So I basically I was going to ask the same question, but I just wonder then, when you said at the beginning slide, you said you summarized EPR, and basically the last conclusion was that physical quantum mechanics is incomplete.
Right.
Okay. If you were to change the period at the end of that sentence and say quantum mechanics is incomplete according to the viewpoint of a realist, would you? Because from what I gather from your argument,
yes,
this gentleman is that
yeah.
the reason there's a problem because EPR couldn't get into the heads of quantum mechanics, right? They couldn't accept sort of all of the subtleties or whatever, right? But even if you did, I mean, it seems to me that no matter what you conclude, there are things, as you say, there are quite crudely you can't conclude. So from the person that's standing on the mainland, right, a realist, then EPR is correct.
Well, I guess one thing I wanted to do is quiz you on exactly what you mean by a realist.
Okay, yeah.
Realism comes in many, many flavors. If by realist you mean something like this, that when I'm given these conditional probabilities, I must interpret them as, in effect, probabilities about counterfactuals. If that's what you mean by realism, then yeah. But part of the point here is to say that that's a tendentious interpretation of quantum mechanics in the first place. And I add this, but there are very many ways to be a realist. But one way that a realist might want to say is, well, I don't want to be realist about more than I have to be. If I start attributing stuff to the world that there's actually some reason to doubt is really there, or no good reason to think is there, then that's not the kind of realism I want to buy into. Yes, sir.
In your abstract, you mentioned the Bayesian connection. Could you elaborate on that?
Okay, yeah, that was a line that I probably
You don't want to put
no, what I meant was
Sorry about that.
Okay.
Skip it.
See,
That got you.
it's friendly to the Bayesian story in at least this way, that the Bayesians do not want to treat the quantum state as a way of attributing a property to the particle. They want to understand the quantum state in a much more epistemic sort of way. And the picture...
I think it was sympathetic all the way up until this
Okay, I think you're
until this
absolutely
very
right.
transparency.
Yeah. Until this very transparency is a bit about my being willing to say, in some cases, we really can know, at least in an idealized kind of way, we can know that if we were to make this measurement, thus and such would happen, and that in those cases, the only rational thing to do is to ascribe the appropriate eigenstate. Up to that point, I think, yeah, Chris and I agree about virtually everything. Yeah.
Yeah, I just have a comment to make about Raphael's comment. It seems to me that this kind of radical indeterminism, or however you want to put it, is not a conclusion of your argument. It's really
Yes, exactly.
the premise of
Exactly.
it.
Exactly.
You're saying
Yep.
something like
Exactly.
the following. Look, EPR are arguing against people who are, like Bohr, who are
That's
saying
exactly right.
that things are indeterministic in some sense at rock bottom. Einstein said he never could really understand that. So he mounted this argument, which was supposed to show,
Yep.
if I accept your premises, then I can show that quantum mechanics is incomplete in a rather straightforward sense.
Yep.
There are hidden variables of some sort.
Exactly right.
Psi has just
Yep.
left something out, and
Yep.
if you add that in,
Yep.
you'll get the right statistics.
Yeah, exactly right.
So-
That was a much more clear version of something that I tried to say less clearly on the earlier slide. I was sort of saying that the dialectical situation
Yeah.
is that EPR's opponent is someone who is what I'm calling the orthodox indeterminist. And then the question becomes, has EPR given this orthodox indeterminist a reason to
That's
budge? You don't need to assume the indeterminist is stubborn. You don't need to assume that they're not willing to give a position. You just need to take their point of view naturally. And my hunch is that for many people who think about quantum mechanics, maybe working physicists or whatever, it's a pretty natural point of view to start with. And so the question is, have you been given any reason to give it up? So the suggestions that you try. Yes.
It seems to me, though, that the way that EPR, the paper now, is used is it's not from, it's not addressed to someone who's an indeterminist. It seems like that's how it's used. It's addressed to someone who likes to say, the world behaves pretty much like I would expect it to, being a macroscopic being, even at microscopic scales. And what you're showing is that if you actually hold true to the principles of Bohr and indeterminism, and you don't make that leap, then not only is quantum mechanics vindicated, but the EPR argument doesn't even hold water, which was the original point of the paper.
Yeah.
But nevertheless, it can still be used by realists who want to say
Yes.
that
Yes. No, I think that's right. I think that in a way, the way that I was putting it to Chris in the conversation we had is that the bell type arguments have become the icing on the cake. That you've got this point of view that the indeterminist sort of holds, and then working through it naturally, the indeterminist finds that the EPR isn't compelling, and then Bell comes along and says, and by the way, you might have thought, well, there's an alternative here that maybe you just don't like, but it was an available alternative, and then Bell says, no, not even that.
So the point is, if you're already hardcore indeterminist, then this, it's just like the Bell inequality is superfluous. It's like, oh, that's nice. What it's saying is that if you want to try to be more, classically realist, ascribe real properties to things, then you sort of do need Bell.
Right. Well, of course, I mean, at the end of the day, I wouldn't want it to stop here. I mean, I would want the indeterminist to, in no way belittle Bell results. The indeterminist would see them as part of what you have to take into account in developing the consequences of this indeterminism and sort of working out the details. So it would be a very welcome addition to the story. But the indeterminist, as I said, without being dogmatic at all, needn't be moved by EPR, and then Bell can come along and say, oh, and here's more stuff for you to think about how these probabilities and so on all actually work. Yeah. Yes?
You mentioned that Arthur Fine had made a comment that EPR, what Einstein was really talking about in this EPR experiment, didn't depend on consideration of simultaneous values of non-commutative observables.
Yes.
I mean, part of your objection to EPR here rests on the kind of arguments that EPR made in terms of non-commutative observables.
Yes.
So if you take that out, and it's been a long time since I've seen this, but I think Redhead in his book, Incompleteness on Kantian Realism, presents the argument without consideration.
Okay, well, let me just say something very brief. I have not actually gone back and done the work that I need to do to sort of feel really comfortable about what I'm saying, but let me give you my impression at the moment. What Einstein said apparently in the letter to Schrödinger after he saw the EPR paper first, it turns out, many of you probably already know this, that the EPR paper was actually written by Podolsky. It wasn't written by Einstein. And Einstein didn't like the way the paper came out. He said, Fine translates it this way, that the main work was smothered in the formalism. And the argument that Einstein liked was one that depended only on considering, how in the world did I get this first element of reality? And I absolutely agree that if you're prepared to start inferring elements of reality at all, already, there's a worry there. But part of what would come into consideration at that point is the sort of things I was saying about, well, okay, here I am, let's just worry about one quantity. I'm Alice, I measure A, I get AK, and then I think I'm entitled to refer to this counterfactual if P were measured, the result would be PK for the other particle. If I do that, I nonetheless know that if I make my measurement a little bit earlier, I might have got an AJ. And if that were so, then the element of reality over there would be a different counterfactual entirely. And then all of a sudden we get nervous again about whether we're completely comfortable in saying that the no influence condition is satisfied. So I think that even if you stick to just the part of the argument that Einstein liked, there are some worries that come up about whether the no influence condition would be satisfied if you want to infer these elements of reality. You could avoid the no influence problem by not inferring the elements of reality in the first place. If you don't make those inferences about elements of reality, it's not clear how you're going to get the influence problem. If you do make those inferences about elements of reality, then I think you're stuck with some worries about, that's interesting. Not expecting that. Okay. You'll get the, let me see if I can just get this to stop doing this.
Who knows what it might come up with?
I don't think there's anything embarrassing. There is a picture of Perotter's bicycle pack, by the way.
Oh.
Oh, you might recognize that. Sorry about that. So I think that even the version Einstein liked, there are some residual ones.
So, I mean, can you just repeat again briefly, what exactly is the objection that you have? So Alice makes a measurement over in this region on a particle. Let's say she measures, let's say, any up-based spinner.
Yep.
In the EPR argument, they would say then there's an element of reality corresponding to the operator measurement in the
Yes.
spinner in this direction over here, so in the vertical direction downwards. And you're saying that you're not happy with that inference?
I'm not happy with that inference in the first place. I'm perfectly happy with the weak inference to if Bob did make parallel measurement, he did get the opposite result. Yes, I'm perfectly happy with that. What I'm not happy with is the inference that says, regardless of whether Bob actually made a measurement or not, had he made a measurement, he would have.
But how is that different from an ordinary prediction that I would make? So I can say in the future, if you were to make a measurement, then you would have got, then you will get this result.
Well, in the first place, in the future case, as I said, I'm prepared to consider that it might be okay to accept the counterfactual, although I'm not going to insist on it. The two things that make me prepared to consider are, first, that you don't get into any worries at all about relativity. Okay, it's in the causal future. You're not going to have to, if you thought there was any sneaking worry about preferred phrase or grandfather paradox, things of that sort, you don't get that. So that's an objection out of the way. Then is there any kind of positive reason why someone might be willing to ascribe a counterfactual? And the kind of positive reason I gave was, imagine Alice telephones Bob, says, hey, there's a particle on the way there, and if you need a particle that will give you pk with a measure p, tell us what. And Bob would be inclined to believe her and inclined to think that even if he didn't measure the particle, he knows what would happen if he did. So that might add up to a reason for saying, okay, in the future case, I'm prepared to go along with counterfactuals. But none of that reason is present in the spatial separated or the backward-looking case. As I said, I'm not insisting on the future counterfactual. I'm just saying I'm prepared to consider it. Because it seems to me that it's a different kind of case. Does that help or make it worse?
I still have a problem actually seeing the distinction that you're making. I mean, the thing is, in quantum theory, you have to make, when you make, okay, so I suppose this thing is problematic here, this idea of measurement and counterfactual is true.
Okay.
I mean, that's talking about
if
a measurement is were to be made in the future, but I mean.
Good. Here's what I think you're predicting when you're making these quantum predictions. But the sort of model I have to think about is you've got an actual experiment. You've got a bunch of measurements that actually were made, and so think of it kind of looking back on it when you're going to analyze the data. You've got a bunch of actual measurements. You've got a tool in quantum mechanics and the way of manipulating states and so on, or making predictions about what the patterns in the actual data are going to be. But you're not making predictions about counterfactual data, at least not typically.
Okay, so if I've got a state now, I'll write down a series of statements to say if this is measured at this later time, this result will be obtained. So those are the statements you write down.
Exactly right. And then I look at my data, and I say, well, in case 17, I measured A and Bob measured P, and in that case, I know what to expect. In case 18, I measured A and Bob was out for a coffee break. I don't have anything to say about what would have happened, at least in non-future directed case. Okay, well, stick now to the cases where I was space-like separated and backward. In those cases, I made a measurement, Bob didn't. What would have happened if Bob had made his measurement? I no more know the answer to that question than I know the answer to the question in the single particle case. I made my measurement here and got AK. What would have happened if Bob had made the measurement of A back here? Would he have gotten AK? Who knows?
But I think Philip is asking about the future. So I think he's saying there seems to be no effective difference between the one with the box,
Right.
one without the box.
But,
When we
yeah,
talk about
all
the
I'm saying
future.
about the future cases is
That-
that,
is
as I
that
said,
the
if you, is that the?
I think that's.
Yeah, okay, then I guess what I'm saying is that, that, in my mind, then would add up to a reason for not attributing the counterfactual in the future. In other words, if you have worries about attributing the counterfactual in the future, I will go along with you if those worries are strong enough. I have no stake in making the counterfactual claim about the future case. I'm merely prepared to say there's an interesting difference, the difference being twofold. There's no worry about conflict with relativity. And second, I have the possibility of conveying some information to Bob that he might reasonably treat as giving him the basis for some counterfactual claims. And I have no such possibility in the simultaneous case or in the backward-looking case. So they're different in at least those two ways. Whether that adds up to enough of a difference to make it reasonable to make the counterfactual claim of the future, I'm quite willing to negotiate that. Yeah. Okay.
Just an observation. Notice that in a deterministic case, when you've got all your elements of reality and everything's deterministic, then it's perfectly okay to make the inference to the future counterfactual.
Yes.
Because you can say, well, if I had made the measurement a little while ago, can be talking about nothing else having changed, I would have gotten the same result. And so, the element of reality won't be sensitive to that temporal change. So it's okay to say.
That's right.
Because everything is, so to speak, there or associated with elements of reality, or all the it's so really this is. This just sort of underlines the fact that the sort of the logic of the argument has to do with the pointing out what's implicit in a truly indeterministic position. Spelled out in terms of counterfactuals, and using that to point out that implicitly, so in effect what I'm saying is implicitly, one could say that the sort of moral of your argument is that the EPR argument just assumes determinism, because it could only be correct in a deterministic situation.
Right.
So they really, in some sense, sort of assume, even though they don't assume determinism,
exactly. That's right.
and purport to be sort of proving it. As a conclusion of the argument, in effect, the argument only works if they assume what
it's
they
slipped in there, even though they didn't realize they were slipping
even
it
though
in.
that's right.
Yeah, that's
right.
right.
Hidden premise.
So it's,
In effect, it's a hidden premise, and it has to do in the vocabulary here with slipping in some counterfactual method. That's the point where
yes, exactly.
where the indeterminate is just going to say no. Yeah. Okay.
So you haven't really given your own opinion yet, so let me try to goad you into
Sure.
giving it by giving my opinion.
Okay, yeah, okay, well, let me jump to the last slide here, because that will tell you something about my opinion. I can get there. Okay.
Oh, you had that much more shows.
Yeah, they were quick. They were just, some of them were point, coming out at the same time. My opinion is that we should be metaphysically modest. My opinion is that, at least as a useful experiment in sort of foundations of the subject here, it's a really good thing to try for a metaphysically modest interpretation.
Well, that's good, but it depends,
Yeah.
modest in whose eyes. Is an operationalist a metaphysically modest person?
Well,
Or a person
operation,
who's metaphysically very presumptive person, yeah. So in my opinion, is the second one. That they're presuming they can make sense about laboratory operations without having an underlying theory that refers to reality, in terms of which they can explicate what is meant by laboratory operations. That's my own opinion. So based on that, I would say the whole point of a quantum interpretation is an answer to a question: what is a quantum reality?
well,
And
but you see,
I wanted to ask you, what, having gone through all this, it led you to a certain view of the wave function. Does it lead you to a certain view of the to the answer to that question, or does it lead you to the view that that question is meaningless somehow? Immodest, or
Not
something
my,
like that.
no, right. Okay. Look, there's sort of two questions here that one might want to distinguish. There's stuff out there. Absolutely, there's stuff out there. And presumably it has some features, characteristics, however you want to put that. And that may or may not be something that we'll ever get a grip on. But there's a somewhat different question. Suppose that, so I'm conceding at least that much realism. Okay. But suppose nonetheless that we think that whether or not there's more to be said, at least, so to speak, in God's mind or something like that, whatever God knows about these systems, so to speak. What we have is this tool which seems to be fine as far as it goes, and which can naturally be interpreted as making as one of its set of assumptions that typically nothing fixes the outcome of measurements and events.
But that's indeterminism. You can be perfectly realistic and not have it.
Absolutely. Yeah, and
But it's stochastic reality.
absolutely. And so, to that extent, it is this. What I mean is this. Suppose that I, Alice, the intern, say, in a particular case, if A were measured, the result might be AK, and it might not be AK. I'm making truth claims. I'm claiming something about the world. If those claims are true, they're true because the world, so to speak, makes them true. Now that may be kind of thin gruel. It may not give you all you want, but it's not irrealist.
But it's not providing.
But Ellen, your metaphysical modesty is more aggressive even than that, it seems to me, because you're saying that not only are you modest with respect to realist conclusions that you might draw, but you're also modest with respect to anti-realist conclusions that might be drawn. That the issue is one of how much is really required by an interpretation of the generalized probability.
That's right.
Yeah.
So there's all kinds of things I'm bracketing here, but in another mood, I might be perfectly prepared to sort of go along with. Let me give you an analogy here, which may be embarrassing to my philosopher, former teachers and colleagues, but it may be. Look, there's this question about what we mean by cause and effect in the first place. That's going to be one of the issues that there. There's a long debate in philosophy about this, but a position that keeps recurring in the philosophical story is a very minimalist account of this, according to which, look, if we're going to talk about cause and effect, all we can really usefully do is talk about kinds of patterns among events. Okay, now, as I was saying to Chris, in my private religion, when I'm in my privately metaphysical shrine, I don't buy that Hegelian story. The story comes from David Hume. But as a working way to proceed for doing philosophy of physics, I might be perfectly happy to say, yeah, we don't need to commit ourselves to any more than that to get on with the job of saying something reasonable about these theories and we can get some reasonable agreement. I don't have to embrace it. But I can say, okay, if that's the only tune you want to work with, I'm happy to do that. And then if you want to have a further discussion about whether that's the end of the metaphysical story, well, you can have that discussion another time. I don't know if that helps or not.
Well, yeah, it helps me to get a sense of what you believe. It doesn't help me to feel happy with this modest way of thinking about quantum mechanics, because it's not telling us. This modesty is, it's more aggressive even in another way, which is that you told us to be modest about the wave function, that we shouldn't think of the wave function as telling us anything in general about reality, which is, okay, I believe the wave function doesn't exist at all, so I'm happy with that conclusion. But then we want something that will tell us. We want some descriptive language that will tell us, allow us to speak about reality.
But that's fine.
That hasn't been offered,
And
except the measurements and a bunch of things which I claim are circular edited.
Look,
Unless you could speak
Here-
about
here's a
reality.
question.
Anyway, we could argue whether it's circular.
well,
but
well,
if you
here's a
believe,
question. Do you think that in order to get the right story here, to get a satisfactory story, that we need to simply find the right way to think about quantum mechanics as we now have it?
quite possible.
Or do you think that what we need is to tell a fuller story that isn't simply quantum mechanics as we now have it? Which,
Right, so I don't have a strong opinion, but I think the most practical way to proceed is to do whichever one. Try and tell the story consistent with quantum mechanics as we have it. Because that's what we have. And then if we go
B.
what?
Answer A first and then move on to
Yeah, if we see how it fails, if it fails.
yeah, but
then
you
we
see,
get a-
but what I'm distinguishing here is there are some people, let's say, for example, the Emperorians, they want to say, no, if we interpret quantum mechanics itself aright, just quantum mechanics, without adding any Boolean junk or anything like that, or any variables, if we just interpret quantum mechanics right, we're going to get to the grand metaphysical heaven that you want.
Yeah, I'm not saying, if that's what you meant, I'm not endorsing
Right.
that view.
But other
But
people-
just because their view of just quantum mechanics means just the waveforms.
Well, that's
Whereas
what
I
I'm
mean-
taking under the
I mean,
example of someone who says just quantum mechanics will do if we just look at it correctly. If the other people would say, well, we want to keep consistent with quantum mechanics, but we need to add something more to the story. And so you might think of, for example, collapse theories, an example of people like that. Or you might think of Bohmians as an example of people like that. So those people I take to do more than just interpreting quantum mechanics. They're giving a positive program of physics. They're sort of saying, look, I think what really is going on here is more complicated. There's more to be said. But it's not just quantum mechanics that more comes from.
If just quantum mechanics just means the Schrödinger equation and the waveforms, and then I would be in the second camp. I think.
Okay, right.
Because it doesn't. I mean, I think you give a very
Right.
you
Mhm.
very convincingly pointed out that doesn't describe
Right.
reality.
And so if someone wants to carry on with the further program, I mean, the first thing I'm going to say is
I think the operators at the funeral home are telling us
It's time to leave the service.
anyway, the short answer about the Alice is at that point I prefer the expertise of people like you who are actually physicists, as opposed to people like me who just be telling stories. You know.
Why don't we carry the discussion if there's more out of to the bistro, and thank Alan for an absolutely clear talk.
Thank you.